Today we're going to graph functions if all we know is the leading coefficient and the factors. If I had x minus 4 and x plus 2, where does that graph hit the x-axis? Positive 4 and then negative 2. And it's a normal shaped parabola. How do I know it hasn't been stretched or shrunk? There's nothing here. So that would be just a normally shaped parabola. Okay. What if I put a 2 in front? It would be 2 times as tall. Are the roots going to change? No. So what happens is this vertex is going to go twice as low as it was before, and it's still going to hit here and here, which makes it much, much steeper. No, and the book wants you to graph them a little more accurately than what I'm going to require. So just know that a normal parabola is shaped like that. A shorter parabola would be something like that, or a skinnier parabola, and I'm not going to be very specific on exactly how skinny or, right? Really, you need to get the direction right, and you need to get the roots right. Okay? What if instead of a 2, I were to turn this into a 1/3? So we would take the distance of the vertex and cut it into thirds, and that would be the new vertex. And it still has to hit the roots, so it would end up being very short. Okay? All right. What if I had negative 4 out front? So that vertex is going to go from here to here, and then 4 times as tall. So that parabola is going to look something like this. Does that make sense? Okay. And this is an x squared. How did I know it's an x squared? There are only 2 x's. Right? There's an x in the first factor and an x in the second factor. What if I had 3 factors? That's an x to the third graph. Okay? Where is this graph going to start? Is it going to start on the bottom or at the top? It's going to start at the bottom. How come? Well, do you remember when we had positive slopes and negative slopes? This is sort of like a positive sloped x to the third. It's going to begin at the bottom and end at the top. Right? So, and the same is true of x to the 5ths and 7ths and 9ths and 11ths. Okay? What about the even numbers? What does a positive even number look like? Both sides go up. A negative even, both sides would go down. That's true of x squareds, x to the 4ths, x to the 6ths, and so on. Okay? So, this graph, it's going to hit at negative 4, and at negative 1, and at 3. Right? And if on the left side, do I start at the bottom or the top? The bottom. So if I'm going in this direction, there's only one way to draw the graph. I have to go through this one, and through this one, and then through that one. Yes? We always start on the left, and this one is a positive slope because this is a positive 1. And all positive slopes have this general trend. Okay? But let's say I change this and I put a negative 2 out front. What is that going to do? Well, every hump is going to double in distance. So this hump is going to flip upside down to here, and then it's going to double and go to there. And this hump is going to flip to here and then double to there. So now I have all of these other points to hit. This point, this point, this point, this point, and that point. And I have to start at the top because it's a negative slope, and negative slopes go in that direction. I'm going to come through and up and down. Does that make sense? Okay. What about this? 1/3 x plus 1 x minus 2 squared. So what sort of graph is this? Is it a quadratic, a cubic, a quartic? Nope. It's a cubic. It's x to the third. Because I have one root there, and then I have two roots there. So this is an x to the third graph, and it's negative. So the slope is that direction. I know it hits at positive 2 and at 1, but I also know something else. What happens at negative... Oh, oops. I got that backwards. So it should be -1. That was bad. Should be -1 and positive 2. But what happens at positive 2? It bounces. So this point is a bounce. So my slope... Oh, geez. That's what I meant. Are you guys all sorts of confused because I messed it all up? I'm sorry. -1/3. So the slope is negative. And it hits positive 2 and -1. I'll get this right eventually. So I need to start in this direction. So I come down. What happens at -1? Go right through. Right through. What? And then I got to come back up. What's going to happen at 2? It's going to bounce off and then go in that direction. Okay. What would the 1/3 do? Make it shorter. So we take this height and we cut it into a third, and then that's just a bounce. So now it looks more like that. Does that make sense? Okay. 6 times x minus 3 times x plus 1 times x plus 4, and let's square this one. What type of graph am I looking at? This one is an x to the fourth. Okay. And is it a positive x to the fourth or a negative x to the fourth? Positive. So what do the ends look like? This one's going up, and this one's also going up. Okay. And I hit at -4, and at -1, and at 3. What else do I know? -1 is a bounce. Okay. And what else do I know? What does the 6 do? Really, really tall. And remember, an x to the fourth is already taller than a parabola. So a normal x squared would look like this, but an x to the fourth is really tall to begin with. And now it's even more tall, so it's going to go straight through there, probably off the page. And then as I come back up, what's going to happen? I'm going to bounce off that and go down. And then as I come up, what happens at the last one? Straight through. Best W ever. Does that make sense to everybody? Okay. 1/20 x squared times x plus 2 squared times x minus 4. This is an x to the fifth. And an x to the fifth is really tall. But I'm cutting it into a 20th, so that's going to shrink it back down. Let's make it negative just for fun. Because why not? So where do I hit the x-axis? At -2, and that's a bounce. And then at 0, and that's also a bounce. and then positive 4, and that just is a straight through. Where do I start and where do I end? It's a negative, so I'm going to start that way and end in the same direction. Okay. I'm coming down. What happens? Oh, what does the 1/20th do? Makes it shorter, which appears wider. So instead of coming in really steep, I'm going to come in at more of an angle. And I need to bounce off that. And then bounce off that. And then go down. Does that make sense? Okay. Now, that's just an estimate of a graph. And do you notice how I drew this one a little bit taller than I drew that one? Why would I do that? The zeros are farther apart. Yep. And I'm not going to be really picky on how you do that, but this is a distance of 2, so it doesn't have as much time to get high as it comes back down. And then this is a distance of 4, so it's going to rise higher than the other one. Okay. What if those two distances are the same? Then they'll be the same height every time. Okay. Let's do, I'm actually going to need an equation. So let's say we had x to the third minus 10x squared plus 19x plus 30. Without using a calculator, let's graph this. Okay, well, I need to find the roots. What could the roots be? 1, 2, 3, 5, 6, 10, 15, or 30. Does 1 work? No. Does -1 work? You just change the sign of every other one. So it'd be 1 plus 10 minus 19, or sorry, yeah, 1 plus 10 plus 19 minus 30. 1 plus 10 plus 19 minus 30 is in fact 0. So I know that -1 works. 1, -10, 19, 30. Drop the 1. -1, -11, 11. That's 30, -30, and 0. So now I have x squared minus 11x plus 30. And I factor that. And I get x minus 6 and x minus 5. So my roots are -1, 5, and 6. So you go through and every other sign you flip. So I'm going to change that to a plus, and I'm going to change that to a minus, and then just add them together. And if you get 0, then it works. And you don't even have to pay attention to even and odd. Because if you, so let's say instead of changing those, I changed this one and this one, you're still going to get 0. So just, don't change, change. Don't change, change. And you don't have to worry about the exponents. Okay, so these are my roots. It's an x to the third graph. It's positive, so it's going to have a positive slope. I draw the graph, and -1 and 5 and 6. So it's going to look like something like that. Okay. Now in this case, you're not allowed to graph it to guess the roots because that will tell you what the equation looks like. Okay, so you actually have to guess. And you can use Descartes' rule of signs. So if we look at the original function, there's 1, 2 sign changes. So positive, negative, complex, 2, 1, 0, or 0, 1, 2. Now, the ones that I'm going to give you today, they have to have the correct number of roots. There's no complex roots because you wouldn't know how to graph it. Right? So let's try another one. x to the third, oh no, sorry, x to the fourth plus 4x to the third minus 11x squared minus 30x. What are my roots? One of them is, say it, 0. Why is one of them 0? I can take out an x. There's no constant. So I know that x could equal 0, and all I have to do is change these. And now the other ones are 1, 2, 3, 5, 6, 10, 15, or 30. Okay, does 1 work? Not even close. That's 5 minus 41, no. What about negative 1? You do 1 minus 4 minus 11 plus 30. That doesn't work. So we got to try something else. What do you want to try? Well, according to Descartes' rule of signs, there is one positive sign change, which means one of the positive ones work. And if you do the negative sign changes, that would be negative plus negative. We have, oh my goodness. I need to rewrite that. It died. It was x to the fourth plus 4x to the third minus 11x squared minus 30x. And we know that x equals 0 is one of them. And I change this to 3, 2, 1, 0. Okay. And we had positive was 1 and negative was 2. So there has to be 2 positives or 2 negatives and 1 positive, because there's not going to be any complex. We don't know how to graph complex. Well, at least not by hand. So what do you want to try? 5. Put 5 in the box. 1, 4, negative 11, negative 30. 1, 5, 9, 45. What do you think? Not going to work. All right, let's try 3. 1, 3, 7, 21. That's 10. And then 30, and we get 0. So I now know that x also equals 3. What about the other two? Just factor it. X plus 5 and x plus 2. So that would be 2 and 5. Oh, negative 2 and negative 5. Thank you. So negative 5, negative 2, 0, and 3. And this is an x to the fourth graph that's positive. So start up. We don't have any bounces. It would look something like that. Okay. Look at 3.8. For number 20, what are you going to do to actually, let's do number 20, because I'm not going to make you do that one. So let's do 20 together. 4x to the third minus 2x squared minus 24x minus 18. What should we do to begin with? Take out a 2. And that gives me 2x to the third minus x minus 12x minus 9. And that's a really good idea, because my original possible answers were all of the factors of 18 and all of the factors of 18 divided by all of the factors of 4. And that's a huge list. But by pulling out a 2, now on this side I get 1, 3, and 9. And on this side I get 2. So my possible roots are plus or minus 1, 3, 9, 1 half, 3 halves, and 9 halves. So I cut my possibles in half at least by taking that 2 out. What is that 2 going to do in the end? Makes the graph twice as tall. Now number 20, all it says is find the roots. But we're going to find the roots and graph it because that's what you'll be doing in the next set anyway. Well, no. I'll tell you when we get there, but no, you won't need to. Okay. Now I need to find possible factors of that. We always try 1. Does 1 work? 2 minus 1 minus 12 minus 9, does that work? No. So let's try negative 1. So I'll switch the second one and I'll switch the last one. 2 plus 1 is 3 minus 12 is negative 9 plus 9 is 0. So negative 1 works. Who didn't understand that? Do you get it now? Whoever it was? I don't remember. Was it you? You get it now? Okay, good. So I know, not working. Negative 1 works. 2, 1, negative 12, and 9. Drop the 2. Negative 2, negative 1. 1. Wait a minute. Did I do something wrong? Oh, yeah. So the original signs were negative, negative, and negative. So negative 2, negative 3, 3, a negative 9, a positive 9, and a 0. So I have x is equal to negative 1. And now I factor this. It will factor, but we have to use the box because there's a leading coefficient. And because there's a leading coefficient, what do I know about my answer? It'll be a fraction. One of them will be a fraction. So 2x squared and negative 9, multiply those together, negative 18x squared. Now, are there factors of negative 18 that add to be negative 3? Negative 6x and 3x. I can pull out a 2x, which gives me x minus 3. And if I pull out an x, I get x plus 3. So what is the root here? 3. And what is the root here? Negative 3 over 2, which is negative 1.5. That's a little bit easier to graph. Now, it doesn't say graph, but I'm going to do it just so I don't have to solve another problem. But my original graph is 2 times taller than I would expect. But there's also a 2 on the inside, so it's actually 4 times taller than I would expect. Does that make sense? So you don't just look at this. It's the original leading coefficient, the original 4. Okay? So negative 1 and negative 1.5 and 3. And it's next to the third. Are we going up or are we going down? Is this a positive slope or a negative slope? It's a positive slope, so we're going to start from the bottom and come up. And I don't have any bounces, but that will have a little hump and then something like that. Does that make sense? Okay. So I want you to do in 3. What is going on? Don't tell me it died again. I can't. I don't know. I broke it. How am I going to? Don't know. Okay, I'll just have to tell you. So I want you to do 3 through 12 all, and then 15. Ooh. 15 to 29 odd. But there's one thing that we haven't done. We haven't done increasing and decreasing, and we need to. So 3.8, 3 through 12 all, and then 15 to 29 odd. And in 17 and through 21, all you're doing is finding the zeros. You don't need to graph. Okay? But once you get to 23, you need to find all of the zeros and graph. And then it says determine where the local maximums and minimums occur, and define the intervals for the function where the function is increasing or decreasing. And that's kind of tough. So once you have drawn the graph, and I'm not sure how the book did it. My guess is they did it the hard way, and we're not going to do it the hard way. We are going to use our calculators. So once you've graphed it, type the function into your... Now it disappeared. Oh, great. Give me that back. Oh, hey, there we go. So graph the function 4x to the third minus 2x squared minus 24x minus 18. Okay, graph. We'll see how good I did. I did a pretty good job, right? So, what is the minimum of this graph? Well, the minimum goes down forever. There is no minimum. What's the maximum? There has no maximum. So we have developed a term for these, and we call them relative minimums or relative maximums, or I think the book actually says local minimums and local maximums, which means when you're nearby that, there is a highest point, right? In that little vicinity, there is a highest point and a lowest point. So we need to find those. Well, we ask the calculator what they are. So after you've graphed it by hand, you can verify your graph on your calculator. And now I want to know what that point is. So second calc, let's do maximum. And it looks like it's about -1, somewhere close to -1. Left bound, I'll type in -2. Right bound, I'll type in 0. And my guess, I'm going to put -1. And I get -1.26, comma 1.06. Does everybody understand that? Okay. Well, this one is called a local max. And this one down here is a local min. Now, I can't see the local minimum on my graph, and that's okay. I know about where it is, right? It looks like it's somewhere in the +1 range. I'll type in second calc, and I will do number 4, or nope, number 3 for minimum. And I'm going to guess from 0 to 3, and I'll guess 1.5. And I end up with 1.59, comma, -45.14. Does everybody understand that? That's easy. The hard part is we want to describe the increasing and the decreasing x values. And what you do is you imagine that this is time. The x-axis is time. During what time periods is the graph going up, and during which time periods is the graph going down? Well, how many up time periods are there? There are two of them. They're this one, that piece, and this piece, right? How many down time periods are there? Just one, that piece right there. So we need to split the x-axis into 3 time pieces. 2 of them represent time when the graph is going up, and 1 of them represents time when the graph is going down. So I could write increasing from negative infinity, if I can draw it, to this number, negative 1.26, and parentheses on both ends, right? Is it going up at negative 1.26? No, it's flat. Right? If you're driving a car, you're going up the hill, up the hill, up the hill, up the hill. When you get to the maximum, you are perfectly level, and then down the hill, flat, and then up the hill. We're going to union that with the other piece, this piece here, which is from 1.59 to positive infinity, and both of those get parentheses. What would decreasing be? From negative 1.26 to 1.59. Okay? All right. Let's say I had a 1/5 x to the 4th equation, and I ended up with 1/5 times x plus 1 times x minus 3 times x plus 5 times x. And 5th might not be enough. Let's do 1/25. Okay. What does that graph look like? Well, it hits at negative 5 and at negative 1 and at 0 and at positive 3. Okay. And what do the ends look like? Are they both up or are they both down? They're both up. And there are no bounces, so something like this. This would probably be down further. Yeah, that's an x to the 4th would be really tall. So something like that. Let me graph it. Ooh, no, that's not what I wanted to do. So x plus 5. Oops. I did it again. X minus 3 and x plus 1. Something like that, right? So I need to find all of the local minimums and all of the local maximums. So second calc minimum, it looks like negative 1, 2, 3.5. So negative 4, negative 3, and negative 3.5. And I get negative 3.7, comma, negative 3.5. Okay, and then there's one here. That's a maximum. And it looks like about negative 1/2. So negative 1 to 0, and I'll guess negative 0.5. And that point would be negative 0.5, comma, 1.6. And then this point looks like it's about 2, and it's a minimum. So 1, 3, and 2. And I get 1 point, or we'll call that 2. 2, comma, negative 1.7. Now we need to break this up into increasing and decreasing. How many decreasing segments are there? So this is a decreasing segment, and this is a decreasing segment. And then that is an increasing segment, and that is an increasing segment. We need to divide up the entire x-axis into increasing or decreasing. So increasing are those blue marks from here to here, which would be from negative 3.7 to negative 0.5. Union with the other chunk, which is from here over to infinity. And then the decreasing segments are from everything up to there. So decreasing would be from negative infinity to negative 3.7, and we'll union that with this chunk here, which is from negative 0.5 to 2. Does that make sense? Okay, so remember 17 to 21, you don't need to graph them. You just need to find the roots. And then 23 through 29, you find the roots and you graph. And then once you have the graph, you plug it into your calculator and you find the local minimums and maximums, and then you divide up that x-axis into increasing and decreasing. All right, get to work.